Welcome back, and having discussed complex numbers, there is an important definition that we are going to make use of, and this video is going to be really short, but we want to talk about rotation scaling matrices. And as you might guess, they are going to be matrices that do what? They rotate and they scale. Okay, spoiler alert, we'll get there eventually. Okay, but if we have a matrix that is 2 by 2 and we have complex eigenvalues for them and eigenvectors, okay, then what we can do is you remember that we can look at similar matrices and do all that stuff and blah blah blah. What happens is that if we have matrix A and we make it, if we want to diagonalize it, right, the process or the way in which we create the diagonal matrix is just going to be as simple as taking the A and B values from our complex eigenvalue and arranging them as such. AB minus BA. Okay, that's what it'll equal in its diagonal form. So it isn't completely diagonal because we have complex eigenvalues, but that's the general form. Now, if we were to find out what S was, this is a little interesting. So notice that there's V plus IW. What we end up doing in S when we create it is we list the complex component first, followed by the real component. Okay, so that's just a little bit new. Okay, and if you want to see the book for the definition or the proof, please do so. Okay. So just an example here, we have A, we want to find S, blah blah blah. Okay, so via the above definition, really, we can look at the determinant of minus lambda for minus 1 minus lambda. Okay, and down along the road, okay, do this and set it equal to 0, blah blah blah. You get lambda is equal to plus or minus 2i. Okay. And then when we look at the kernel of minus 2i and then 4 and minus 1 and minus 2i, okay, for the eigenvector, okay, what we end up getting is the matrix 2i, or the vector, sorry, 2i and minus I. So then if we break this into real and imaginary components, this would be, 2i and 1, my bad, negative 1 at that. So it'd be 0 minus 1 would be the real, and then plus I times 2, 0. Okay, so then this is the V plus IW form. So then that means that S is going to be the matrix 2, 0, listing the imaginary first, followed by 0 minus 1. Okay, and then if I were to compute SA S inverse, or S inverse AS rather, this ends up being, okay, and you might imagine we would have 0, 2, right, for our eigenvalue had 0 in the real, 2 in the imaginary, and then we list it in the opposite for the diagonal form. We could also write it as, and we will come to need it as, factoring out the 2 and then 0, 1 minus 1, 0. Okay, we will see why that is so important later. Okay, and so if we wanted to, we could write this matrix as a scalar times a rotation matrix, and I think I have done just that. But the only thing is, this isn't quite clear which rotation matrix it is. So if we again look at just 0 minus 1, 1, 0, and we want to write that as a rotation matrix, this would be cosine of pi over 2, sine of pi over 2, and then minus sine pi over 2, and cosine of pi over 2. Okay, and so there we have it. So that's why we can view this S inverse AS as a rotation scaling matrix. So we'll see this pop up in the next video, and we'll make use of it quite a lot when we're dealing with behavior of dynamical systems that have complex eigenvalues.